Okay, so here's a nice little demonstration how neurons communicate. We're going to start at the dendrites. Up close view, better view. Inside our postsynaptic neuron, we have a negative charge. Outside is positive. Our neuron channels are going to open. Our positive molecules are going to enter. And the inside becomes more positive. So here we go. We have all these positives. They come together. What just happened right there? Ooh, right before action potential. When they all come together, we add them up. Summation. So summation happens. There they go. It's a nice positive. Action potential happens. We're going to follow it going down the axon, down the axon, down the axon to the terminal buttons. Up close view, up close view. Action potential causes the vesicles to start moving. They dump neurotransmitters into the synapse. They go across the synapse, attach to the receptors, which makes them open. Positives come in, and on, and on, and on. Pretty cool, huh? Inhibitory potential. So say we don't get all these positives like we just got the last time. How many positives do we have? How many negatives do we have? 3. They're going to come together. If we add them all up, we're left with 1 positive, which is not going to be enough for an action potential, so nothing's going to happen. So we get some more positiveness coming in. Some more animation. Just for those of you who are visual. So here we go. We're going to speed this up a little bit. If you take a look, this pink and this purple are what? Receptors or ion channels. There you go. So here we go. We have our ion channels. These purple and pink things are sodium and potassium. So here we go. What's going to happen first? What's going to rush in? Sodium. Sodium's going to come rushing in. Do you see that? There's our action potential. Shink. Sodium comes rushing in. What's happening now with the purple? Potassium starts going out. What just happened there? The gates closed. Which gates? Sodium. Sodium gates closed. What's happening with the purple? Still going out. Still going out. Until finally, tink, they close. Does that help? Do you like the visual representation? Here's about the nerve.
Current that travels along dendrites or axons due to ions moving through voltage-gated channels in the neuron's plasma membrane. Voltage-gated channels open and close in response to an electrical voltage, so they are affected by changes in electrical charge around them.
Some of these is going to be big whippity talk. You don't have to pay attention to that.
Maintained between the inside and outside of the cell. This charge difference is produced and maintained largely by active transport using sodium-potassium pumps. The pumps send sodium ions out of the cell and bring potassium ions in, while other channels allow some flow of potassium ions back out of the cell. The sodium ions cannot easily get back in to replace the lost positive charges. The overall result is that the exterior of the cell has a net positive charge and the interior has a net negative charge. The difference in charge between the interior and exterior of the cell is called the resting membrane potential. A nerve impulse begins when a stimulus disturbs the plasma membrane on a dendrite, causing sodium channels to open. Sodium ions flow into the cell, lessening the charge difference at that location. If the change is enough, it will cause nearby voltage-gated sodium channels to open. This allows so many sodium ions to flood into the cell at that location that the membrane there is depolarized, with the local region inside the cell having a net positive charge and the outside of the cell having a net negative charge. This affects neighboring voltage-gated sodium channels, which then open, moving the depolarization along the membrane. This moving depolarization is called an action potential. Changes occur behind the action potential to restore the resting membrane potential. The voltage-gated sodium channels close and voltage-gated potassium channels open. This allows a rapid flow of potassium ions out of the cell, repolarizing the membrane so that the inside is again negative and the outside positive. This is followed by use of sodium-potassium pumps to fully restore the resting membrane potential and to reestablish proper concentrations of sodium and potassium ions inside and outside the cell.
So there's the depolarization. That's the wave that we did. One last one for you.
Action potentials arriving at the presynaptic terminal cause voltage-gated calcium ion channels to open. Calcium ions diffuse into the cell and cause synaptic vesicles to release acetylcholine, a neurotransmitter molecule. Acetylcholine molecules diffuse from the presynaptic terminal across the synaptic cleft and bind to their receptor sites on the ligand-gated sodium ion channels. This causes the ligand-gated sodium ion channels to open and sodium ions diffuse into the cell, making the membrane potential more positive. If the membrane potential reaches threshold level, an action potential will be produced.
There you go. So there's the chemical communication.
So that's all that we have for electrical and chemical communication.